Most people looking for diamonds are looking for something that sparkles, something that looks expensive before it has been touched by anyone. That is not what a diamond looks like in the ground. A rough diamond sitting in a gravel bar or embedded in host rock looks like a dull, waxy, slightly translucent pebble that you would walk past without a second thought. The shine comes later. What you need to identify first is not the diamond itself, it is the rock that carries it. There are specific rock types on this planet that contain diamonds, and only those rock types. If you are not standing near one of them, you will not find a diamond regardless of how carefully you look. Understanding which rocks those are, what they look like in the field, and where they occur in the United States is the entire difference between searching with a real chance and searching in a place where no diamond has ever existed. The primary rock that carries diamonds from where they form, deep in the Earth's mantle to within reach of the surface, is called kimberlite. It forms in carrot-shaped pipes that narrow as they go deeper, and it reaches the surface through what were essentially violent, fast-moving volcanic events that happened millions to hundreds of millions of years ago. In the field, fresh kimberlite has a distinctive blue-gray to greenish-gray color, and a texture that is softer and more crumbly than most hard rocks. Miners who worked the South African pipes in the 19th century called it blue ground, and the name is accurate. It looks nothing like granite. It looks nothing like basalt. It has a somewhat earthy, almost clay-like quality where it has been exposed and begun to weather, and that weathered surface turns yellowish-brown over time, which is why miners called the upper portion yellow ground. Kimberlite is also unusual in that it contains a chaotic mixture of fragments from different rock types embedded within it, pieces of material the rising magma picked up on its way through the crust. If you find a rock that has a greenish-gray, somewhat soft matrix and visibly contains angular fragments of completely different rock types mixed into it, you are holding something worth investigating. That texture, a mix of different materials in a fine-grained, softer matrix, is one of kimberlite's most recognizable field characteristics. The pipes themselves erode slightly faster than the surrounding harder crystalline rock, which means they often form subtle depressions in the landscape. In areas where kimberlite is documented, experienced surveyors look for gentle circular to elliptical low spots in the terrain, where the ground is softer and the vegetation grows differently than the surrounding area. The pipe is not always obvious, but the topographic signature is often there if you know to look for it. The second diamond-bearing rock type is lamproite, which is what the site in Murfreesboro, Arkansas is made of. Lamproite is chemically different from kimberlite, but formed by the same general process, a deep mantle magma ascending rapidly to the surface and carrying whatever it picked up along the way, including diamonds. In the field, lamproite is harder to recognize than kimberlite because it weathers into surfaces that look more like ordinary volcanic rock. It tends toward a yellowish to orangish-brown surface color after weathering, with a fine-grained texture that can look almost like hardened clay in some exposures. The Crater of Diamonds site in Arkansas is the surface of a lamproite pipe that has been exposed by millions of years of erosion. The pipe is approximately 95 acres across at the surface. The park plows the surface regularly to keep fresh material turned up, and visitors search the plowed soil directly. That site is the only place in the world where you can search for diamonds in their original volcanic deposit and keep what you find. Since it became a state park in 1972, visitors have found more than 35,000 diamonds. The largest found by a visitor in recent decades weighed 8.52 carats, found in 2020. A 4.49 carat diamond was found by a visitor in 2024. These are not edge cases. Diamonds surface at that site multiple times per year because they are literally distributed through the volcanic rock underfoot. What makes Crater of Diamonds different from every other location where diamonds have been found is that there is no concentration happening. No river has sorted the diamonds and gathered them into traps. They are simply present in the lamproite at the same low concentration they were in when the pipe formed. Searching there requires patience and the ability to recognize a small, waxy, non-sparkling crystal for what it is before you put it back down. If kimberlite and lamproite pipes are the source, then the rocks downstream from those pipes are where diamonds end up after millions of years of erosion. This is what a placer diamond deposit looks like: river gravel that has been sorting heavy minerals for a very long time. Diamonds have a specific gravity of approximately 3.5, which makes them denser than almost all common river minerals. Quartz sits at 2.65, feldspar at around 2.6. Even most garnets, at 3.5 to 4.3, are in the same range. What this means in a river system is that diamonds concentrate in the same locations where other heavy minerals concentrate: behind large boulders in the streambed, on the inside curves of bends, in potholes and depressions in the bedrock, in the coarser fraction of gravel deposits rather than the fine sand. The gravel you are sorting through in a placer diamond search is not random gravel. You are specifically looking at the heavy fraction, the material that settles and stays when the current is moving most of the lighter grains downstream. Experienced prospectors working placer diamond ground use a pan in the same way gold panners do, washing off the lighter material and examining what remains. The material that remains is where diamonds will be if they are present. If kimberlite and lamproite pipes are the source, then the rocks downstream from those pipes are where diamonds end up after millions of years of erosion. This is what a placer diamond deposit looks like: river gravel that has been sorting heavy minerals for a very long time. Diamonds have a specific gravity of approximately 3.5, which makes them denser than almost all common river minerals. Quartz sits at 2.65, feldspar at around 2.6. Even most garnets, at 3.5 to 4.3, are in the same range. What this means in a river system is that diamonds concentrate in the same locations where other heavy minerals concentrate: behind large boulders in the streambed, on the inside curves of bends, in potholes and depressions in the bedrock, in the coarser fraction of gravel deposits rather than the fine sand. The gravel you are sorting through in a placer diamond search is not random gravel. You are specifically looking at the heavy fraction, the material that settles and stays when the current is moving most of the lighter grains downstream. Experienced prospectors working placer diamond ground use a pan in the same way gold panners do, washing off the lighter material and examining what remains. The material that remains is where diamonds will be if they are present. If kimberlite and lamproite pipes are the source, then the rocks downstream from those pipes are where diamonds end up after millions of years of erosion. This is what a placer diamond deposit looks like: river gravel that has been sorting heavy minerals for a very long time. The indicator minerals are where field identification of diamond-bearing ground actually starts for anyone working systematically. 4 minerals travel from the same deep mantle source as diamonds and appear in stream sediments wherever kimberlite or lamproite has been eroding upstream. The first and most useful is pyrope garnet. Most garnets you will find in river gravel are reddish-brown almandine garnets from regional metamorphic rocks. Pyrope garnets from kimberlite are different. They tend toward a deeper red to almost purple color, and the specific type associated with diamond-bearing kimberlite has a chemical signature: high chromium and low calcium, that can be confirmed analytically, but that often produces a recognizable purplish-red color in the field. They are also rounded because they have traveled long distances, and they are dense enough to stay in the heavy mineral fraction of river sediment. Chrome diopside is the second indicator. It is a pyroxene mineral with a striking emerald green to bright green color that stands out against the gray and brown background of river gravel. It is not common in river systems that do not drain kimberlite or related deep source rocks. When you find bright green rounded crystals in your heavy mineral pan concentrate in an area with the right geological background, you are looking at chrome diopside, and that is worth noting. Ilmenite and chromite are the other two. Both are black, heavy, and dense. Ilmenite from kimberlite has a specific magnesium content that distinguishes it chemically from ilmenite produced in other geological settings. But in the field, both black minerals concentrate with other heavies, and their presence in high abundance alongside pyrope garnet and chrome diopside builds the indicator picture. None of these minerals individually confirms a diamond source. Together, they describe a heavy mineral assemblage that is characteristic of kimberlite drainage. Following that assemblage upstream is how new kimberlite pipes are found. You sample stream sediment at different points along a drainage, where the indicators become more abundant and the grains become more angular and less rounded by transport. You are moving closer to the source. Geologists used exactly this approach to discover the major diamond fields in Canada's Northwest Territories in the 1980s and 1990s, which turned into some of the richest diamond deposits ever found. The method works. When you are actually handling material in the field, either at an established site like Crater of Diamonds or in gravel draining a Kimberlite region, knowing what a rough diamond looks like is essential because nothing about it resembles a cut stone. Most natural rough diamonds are octahedral in form, 8 triangular faces making a shape like 2 four-sided pyramids joined at the base. They also occur as cubes, as rounded dodecahedra, as flat triangular macles that form by twinning, and as irregular shapes that result from partial resorption during their travel through the mantle. What they all share is a distinctive surface luster called adamantine luster, which comes from diamonds' extremely high refractive index of 2.42. Adamantine luster looks different from the waxy luster of quartz or the resinous luster of garnet. It has a high gloss, almost greasy quality that seems disproportionate to the stone's small size. A rough diamond in a gravel bar catches and reflects light in a way that makes it stand out when light hits it at the right angle. This is what the experienced searchers at Crater of Diamonds are trained to notice. Not a sparkle the way a cut stone sparkles, but a specific quality of reflected light from a small, often pale or slightly yellowish or brownish waxy crystal with adamantine luster, and an octahedral or rounded cubic shape in the right geological context is worth setting aside for a proper test. The definitive field test is hardness. Diamond is a 10 on the Mohs scale, meaning nothing will scratch it. If you draw a piece of corundum across the surface of a suspected diamond and the corundum leaves a scratch, it is not a diamond. If it does not, you have narrowed the field dramatically. Combine that with the fact that diamond is an excellent thermal conductor, giving it a distinct coldness against your lip compared to glass or quartz, and you have 2 field tests that together can eliminate most other minerals. The Great Lakes states produce diamonds through a completely different mechanism that most people in those states have never heard of. Wisconsin, Michigan, Indiana, and Ohio all sit on top of glacial sediment deposited by ice sheets that moved south from Canada during the Pleistocene ice ages. Those ice sheets pass directly over kimberlite fields in Ontario and Quebec that are now documented diamond-producing regions. As the glaciers moved, they eroded those kimberlite fields and transported the material, including diamonds, hundreds of miles south before depositing it as glacial till and outwash gravel. The concentrations are extremely low, but the diamonds are there, distributed through glacial sediment across a large area of the northern Midwest. The largest diamond ever found in the continental United States, outside of Arkansas, was found in Wisconsin. It weighed 21.25 carats rough and came from glacial gravel. Searching glacial till for diamonds is different from searching placer river gravel because the material has not been sorted by hydraulic processes the way river gravel is. The concentration in any given scoop of glacial till is lower, and there are no predictable heavy mineral traps to target. What you can target is the coarser fraction of glacial outwash in drainage systems downstream from the original till deposits, where secondary reworking by streams has begun to create partial concentration. In Wisconsin's Waukesha County and in parts of Michigan's Upper Peninsula, this is exactly the type of material where glacial diamonds have been found. The full picture of where diamonds occur in the United States is larger than what most people understand, because a significant portion of the country has never been systematically surveyed for indicator minerals. The State Line District was found because somebody decided to look carefully at stream sediments in that area. Canada's Northwest Territories diamond fields were found the same way. The process is not complicated. It requires going to the right place, sampling the right material, and knowing what the indicator assemblage looks like in a pan, and what a rough diamond looks like when it is sitting in the dirt next to a piece of quartz and a piece of garnet. That knowledge separates the people who find diamonds from the people who walk past them. It's the same knowledge that the collectors, the geologists, and the long-term prospectors who have actually recovered diamonds in this country carry with them every time they go into the field. It's not secret, it's just specific. And now you have it.